Welcome back to our series on systems modeling. In the last module, we introduced basic concepts around systems, defining some basic components and characteristics of these systems. In this module, we're going to look at some simple models of population dynamics using a systems perspective. Upon completing this module, you should be able to represent simple population dynamics conceptually in systems diagram, translate these conceptual models into mathematical form, and predict the dynamic behavior of these systems. In this module, we will start developing mathematical models not by fitting data, but by trying to capture the fundamental processes driving system behavior. In short, we are transitioning from the realm of empirical models into more mechanistically based process models. Very often, the models we explore will describe trajectories of change, the dynamic behavior of the system through time. And we will generally use differential equations to describe these dynamics, for the simple reason that differential equations capture how one variable changes with respect to another. For the models we will be exploring in the next few modules, the differential equations will describe changes in our stocks, or state variables, with respect to time. This approach is a powerful one that can be applied to a wide variety of dynamic systems. We note that we will be looking at two types of dynamic models. Some of our models will be linear and some will be nonlinear. Here, linear or nonlinear has a slightly different meaning than it did when we were describing regression techniques, where linear meant linear with respect to the model parameters. Here, linear means described by a linear differential equation, meaning a differential equation whose terms are either linear combinations of the state variable that are captured by the model or constants. Conversely, nonlinear models are those whose state equations contain nonlinear terms. Linear models have a distinct advantage in that they can generally be solved directly. However, many phenomena in ecosystems, hydrology, and other types of systems of interest to ecological engineering are inherently nonlinear, so we will need to develop numerical methods to solve these models. Population models provide some good examples of simple linear models, so let's look at one of these. Our first model is exponential growth. This model captures the idea that a population grows according to a per capita growth rate that is constant through time and is unaffected by resource or density constraints. The conceptual model is simple. A population can reproduce at a rate that is proportional to the population size at any given time. The proportionality constant is the per capita growth rate. Further, it assumes that no other processes contribute to or remove from the population. Here is the system diagram for exponential growth. It consists of a single state variable, the population size, with a single process, growth, influenced by the current population size and the per capita growth rate constant, k. The system contains one positive feedback loop, giving us a pretty good idea of what to expect in terms of system behavior. Mathematically, we can capture this conceptualization with a differential equation describing the rate of change of the population. Translating the conceptual model, saying the rate of population change is proportional to the current population size, becomes dn dt is equal to kn, where k is the proportionality constant, the per capita growth rate. Note that k has a physical meaning, unlike many of the parameters we observed when looking at strictly empirical models. This is a common situation in mechanistic models. Because these models are based on real-world processes, their parameters often have real-world meanings. Because this is a linear model, because the only model term, k, n, is a linear combination of k and n, we generally can anticipate solving it analytically, integrating the differential equation to a closed-form solution. For exponential growth, the solution is straightforward. We separate the differentials and integrate both sides, resulting in a closed-form solution providing the predicted value of n at any given point in time. We've had to introduce the constant of integration, n0, that also has a real-world interpretation. It represents the initial population size at the start of the simulation. Given n0 and k, we can predict the size of the population at any future time t. Note that even though this is a linear model, the model response follows a curve. Being a linear model in no way implies the model response will be following a line. In this case, it will increase forever at an ever-increasing rate, leading to runaway growth. This is an example of a positive feedback loop with no balancing feedbacks to stabilize it. Now that we have a model, we can begin to answer some questions about model behavior. For example, how long will it take a population to double in size? To answer this, we let n equals n0 times 2, double the initial population size, and solve the model for the time at which this condition is met. We then rearrange the model equation highlighted on the slide above, solving for t. This form makes it clear that doubling time is a function only of the per capita growth rate constant and is independent of the population size, which makes perfect sense if you think about it. Suppose we have a population data set that we wanted to fit to this model, containing population sizes at various points in time. There are two parameters in this model, k, the per capita growth rate, and n0, the initial population size that we would need to estimate from the data. How would we do this? We've seen how, in previous modules, regression, specifically nonlinear regression, since our model equation is nonlinear with respect to the parameter k. Technically, we could transform the model equation into linear form with the log transform, allowing us to use linear regression on the transformed equation. However, nonlinear regression would be preferred in this case and would provide a slightly better fit to the data. The exponential growth model has many assumptions and limitations that may or may not hold up to real-world scrutiny in some situations. High among these is the assumption that the population can continue to grow forever, which obviously is not possible with any real population. One modification we can make to address this is to add an additional term to the model that limits the rate of growth as the population approaches some maximum size, termed the carrying capacity. Here's the system diagram for logistic growth. Note the addition of the density-dependent parameter Nmax, the carrying capacity. This provides a negative or balancing feedback loop to the system. The logistic growth model assumes that the relative growth rate declines linearly with population size. This results in the equation highlighted here. Note the kn term is the same as we've had in exponential growth, but we modify the exponential growth rate by scaling it to the inverse of the population size, the 1 minus n over nmax term in the differential equation. As the population gets larger, the growth rate is reduced proportionally. The model captures the idea that a population grows exponentially at relatively low population size, but becomes limited as resources become scarce as a result of the increasing density. Is this model linear or nonlinear? It's nonlinear because the n squared term resulting from expanding the first and second terms in the state variable raised to a power other than 1 or 0. The exponential portion of the growth is linear, meaning it scales with population size, but the density-dependent term is nonlinear because it scales with the square of the population size. That's why, for a small initial population, it starts off exerting very little effect, but as n grows, the density-dependent term dominates the exponential growth term, shutting down growth. It is also a negative or balancing feedback loop. Increasing density of the population exerts a moderating control on the population. These relationships have important consequences for the dynamic behavior of this model. To solve the logistic model, we need to integrate the model differential equation. This is accomplished through separation of variables, application of partial fractions for the actual integration, and simplification of the result. It's getting messier to solve, but it's still possible to generate a closed-form solution for this model. Even though this is a nonlinear model, an analytical solution exists. This is the exception rather than the rule for nonlinear models. Very often, an analytical solution does not exist. The chart shows the model integrated over time. At low population sizes, the growth rate is dominated by the exponential term, and a higher population is dominated by the density term. How many parameters are in this model? The answer is 3, N0, Nmax, and K, all of which have real-world interpretations. N0 is the initial population size. Nmax is a maximum population size that can be supported by the resource, and K is the per capita growth rate. Now for an exercise on your own. Download the Excel spreadsheet at the location provided on this slide. It has the logistic growth model set up for a simulation period of 0 to 10 time units. Model parameters are in the green cells near the top of the screen. Try guessing what effect the model parameter change will have on the system dynamics, and then enter your model parameter change in the spreadsheet to see if you correctly anticipated the effect. Where on the chart is the growth rate maximized? Hint, this will be where the population curve is steepest, meaning it's increasing the fastest. How would you derive this point where growth is maximized mathematically from the model? Here's another hint. Differentiate the rate of change with respect to time and set to 0. And finally, what happens when n is greater than the carrying capacity? You might want to pause the video at this point, get the Excel spreadsheet, and play around with it a little bit to see if you can answer these questions. Next, let's do a variation on the logistic growth equation that relaxes one assumption, that the effect of the density-dependent term, in other words, the effect of the resource limitation, is instantaneous. In reality, for longer-lived populations, an individual in the population may not exert a significant demand on the resource until it has grown to maturity. We can capture this concept in the logistic growth model by introducing a time lag into the population that is affecting the density term, n over n max. This has the downside of making the analytical solution very difficult, beyond the scope of this module. We will solve this one numerically using a technique called Euler's method that we will cover in a later module. Let's do one more exercise. Using the same spreadsheet you previously downloaded, switch to the tab titled Logistic Growth with Time Lag. You can see the tabs at the bottom of the spreadsheet. Again, we will run a simulation for 10 time units, but this spreadsheet is set up for a 0.5 time unit time lag in the density effect. Keeping the N0 and Nmax values the same, try changing the values of K, the per capita growth rate constant, to 2.0. What happens? Next, try a value of K of 3.0 and observe what happens. What about 4.0? Finally, try a value of 4.8 and observe the response. What do you think is going on here? As the system is sped up with increasing K values, the exponential growth term increasingly dominates the density effect term. More importantly, with the time lag, the information feedback of the population size in the density effect feedback loop is delayed, and the system becomes increasingly more unstable as a result. At K values above 4.8, the system becomes completely unstable and effectively crashes. This would be a good time to pause the video, switch to the second tab on the spreadsheet, and play around with the K values described above. To recap, in this module, we examined some simple population models as a way of beginning thinking about implementing mechanistic models. First, we can represent systems dynamics using differential equations. Population models provide some good examples of this, providing a mathematical form that naturally describes how one variable changes with respect to another. For describing population dynamics, we consider what processes add to the population and what processes remove from the population. This approach is broadly applicable to systems that conserve mass or energy and provide a mechanistic basis to the models we examined. Third, we saw that populations benefit from regulatory systems balancing positive and negative feedback loops. This is true of virtually all systems, and we saw an explicit example when comparing exponential and logistic growth functions. And finally, we saw that as feedback loops become disconnected in time or space, a system can become unstable. This is particularly true in simple systems that do not have sufficient regulatory feedback loops. In our next module, we'll be looking at some nonlinear systems and describing solution techniques for solving these systems.